Hello and welcome to Lesson 12 of the Big Data and Hadoop Developer course offered by Simplilearn. This lesson will focus on the Hadoop ecosystem and its components. Let us explore the objectives of this lesson in the next screen. By the end of this lesson, you will be able to explain the structure of the Hadoop ecosystem and describe the different components of the ecosystem along with their roles. In the next screen, we will focus on the Hadoop ecosystem. The image on the screen displays the various Hadoop ecosystem components as part of Apache Software Foundation projects. Please note there are many other commercial and open source offerings apart from the Apache projects mentioned on this screen. The Hadoop ecosystem components have been categorized as follows: file system, data store, serialization, job execution, work management, development, operations, security, data transfer, data interactions, analytics and intelligence, search and graph processing. Click each section of the image to learn more. Now we will focus on the security components, which are Knox and Sentry. Knox is a system that provides a single point of secure access for Apache Hadoop clusters. Sentry is a system for providing fine-grained role-based authorization to both data and metadata stored on an Apache Hadoop cluster. Both these projects are currently in the initial release phase. Let us now discuss the components related to data interactions. These are as follows. Pig is a platform for analyzing large data sets that consist of a high-level language for expressing data analysis programs, coupled with infrastructure for evaluating these programs. Hive is a data warehouse system that facilitates easy data summarization, ad hoc queries, and analysis of large data sets stored in Hadoop-compatible file systems. HCatalog is a table and storage management service for data created using Apache Hadoop. Tez is a generic application framework that can be used to process complex data processing task DAGs or directed acyclic graphs. It runs natively on Apache Hadoop Yarn. It provides SQL queries on top of Hadoop. Gora is a framework for an in-memory data model and persistence with MapReduce support. We will now focus on some more components related to data interactions. They are as follows. Spark powers a stack of high-level tools including Spark SQL, MLlib for machine learning, GraphX, and Spark streaming. Storm is a system to process unbounded streams of data for real-time processing. MRQL is a query processing and optimization system for large-scale distributed data analysis built on top of Apache Hadoop, Hama, and Spark. Tajo is a data warehouse system for Apache Hadoop which supports low-latency, scalable ad hoc queries, online aggregation, and extract transform load process or ETL. The job execution engines are as follows. MapReduce is a framework for performing distributed data processing. It comprises the job tracker, the task tracker, and the job history server. Yarn is a framework that facilitates the writing of arbitrary distributed processing frameworks and applications. Hama is a pure bulk synchronous parallel or BSP computing framework for massive scientific computations such as matrix and graph and network algorithms. The serialization components are Avro, Trevny, and Thrift. Avro is a data serialization system. Trevny is a column file format used to permit compatible independent implementations that read and/or write files in this format. Thrift is a framework for scalable cross-language services development. The file system component of the Hadoop ecosystem is Hadoop Distributed File System, or HDFS. that provides high-throughput access. It is supported by name node, secondary name node, and data nodes in the Hadoop cluster. The data store components comprise HBase, Cassandra, and Accumulo. HBase is a distributed, scalable, and big data store. Cassandra is a highly scalable, eventually consistent, distributed, and structured key-value store. Accumulo is a sorted, distributed key-value data storage and retrieval system. Now let us discuss the components related to work management, operations, and development. The work management components of Hadoop Ecosystem are Oozie and Zookeeper. Oozie is a workflow or coordination system that helps to manage Hadoop jobs. Zookeeper is a centralized service for maintaining configuration information, naming and providing distributed synchronization, and group services. The operations components of the Hadoop ecosystem are Ambare, Vaidya, BigTop, and Whir. Ambare is a web-based tool used for provisioning, managing, and monitoring Apache Hadoop clusters. Vaidya is a performance diagnostic tool for MapReduce jobs. BigTop is a project for the development of packaging and tests and for ensuring interoperability among Apache Hadoop-related projects. Whir constitutes a set of libraries for running cloud services, for example, running Hadoop clusters on EC2. The development components of the Hadoop ecosystem are Crunch, MRUnit, and Hadoop Development Tools, or HDT. Crunch is a framework for writing, testing, and running MapReduce pipelines. MRUnit is a Java library that helps developers unit test Apache Hadoop MapReduce jobs. Hadoop Development Tools, or HDT, comprise Eclipse-based tools for developing applications on the Hadoop platform. Please note, some of these tools may not be under active development or they may not be supported currently by the open source community. Now we will focus on the data transfer components, which are Flume, Scoop, Chukwa, Kafka, and Falcon. Flume is a distributed, reliable service availability for efficiently collecting, aggregating, and moving large amounts of log data. Scoop is designed for efficiently transferring bulk data between Apache Hadoop and structured data stores, namely relational databases. Chukwa is an open-source data collection system for monitoring large distributed systems. Kafka is a distributed publish-subscribe messaging system. Falcon is a configuration of data motion with replication, lifecycle management, lineage, and traceability. Now let us discuss the components related to work management, operations, and development. The work management components of Hadoop ecosystem are Oozie and Zookeeper. Oozie is a workflow or coordination system that helps to manage Hadoop jobs. Zookeeper is a centralized service for maintaining configuration information, naming and providing distributed synchronization, and group services. The operations components of the Hadoop ecosystem are Ambare, Vaidya, BigTop, and Whir. Ambare is a web-based tool used for provisioning, managing, and monitoring Apache Hadoop clusters. Vaidya is a performance diagnostic tool for MapReduce jobs. BigTop is a project for the development of packaging and tests and for ensuring interoperability among Apache Hadoop-related projects. Whir constitutes a set of libraries for running cloud services, for example, running Hadoop clusters on EC2. The development components of the Hadoop ecosystem are Crunch, MRUnit, and Hadoop Development Tools, or HDT. Crunch is a framework for writing, testing, and running MapReduce pipelines. MRUnit is a Java library that helps developers unit test Apache Hadoop MapReduce jobs. Hadoop Development Tools, or HDT, comprise Eclipse-based tools for developing applications on the Hadoop platform. Please note, some of these tools may not be under active development or they may not be supported currently by the open source community. In this screen, we will focus on Apache Oozie. Apache Oozie is a workflow scheduler system used to manage Hadoop MapReduce jobs. The workflow scheduler provides an option to users to prioritize jobs based on their requirement. Apache Oozie executes and monitors workflows in Hadoop. It also performs periodic scheduling of workflows. Further, Oozie has the capability to trigger the execution of workflows based on data availability. It also provides a web and CLI. In the next screen, we will focus on the workflow of Apache Oozie. The image on the screen depicts the basic mechanism of Oozie Workflow. The x-axis represents the workflow section and the y-axis shows the scheduling section. The structure is systematic so that the user can keep track of the progress of the flow. Consider the first flow in which data is extracted from HDFS using Hive Query Language or HQL and then stored in another location of HDFS. This data is then converted to structured data and stored in MySQL using Scoop. This enables a user to create a systematic workflow for any type of Hadoop or Hadoop ecosystem-related jobs. In the next screen, we will further discuss Apache Oozie Workflow. Oozie has three types of flow mechanisms, namely control flow, action flow, and scheduling. The control flow is responsible for starting, stopping, or killing a job generated in Hadoop. It is also used for decision-making with respect to priority. The action flow is responsible for starting the Hadoop MapReduce jobs that are present in the queue. It can also run custom Python or Java code and manages HDFS input-output operations. It is also used to create threads of a specific process. Scheduling is about providing a mechanism to perform scheduling of jobs. In the next screen, we will introduce Mahout. Mahout is an ecosystem component that is dedicated for machine learning. The machine learning process can be done in three modes, namely supervised, unsupervised, and semi-supervised modes. Click each tab to learn more. The supervised mode refers to focusing on a specific pattern. The unsupervised mode refers to the collection of data based on any pattern found in data. The semi-supervised mode is similar to the supervised mode, with the difference that decision-making is done through human intervention. In this screen, we will discuss why Mahout is important. Machine learning is a challenge because many open-source ML libraries are either research-oriented or they lack community, documentation, and real-time examples, scalability, and Apache license. The goal of Mahout is to build scalable machine learning libraries with an Apache license. In the next screen, we will discuss the features of Mahout. Mahout is a component made to interact with Hadoop services and perform machine learning processes. Hadoop contains HDFS to perform storage and retrieval of data using MapReduce API, which provides scalability and fault tolerance in processing a job. Mahout contains the library of machine learning algorithms. It is bundled with real-time examples of the same. In the next screen, we will focus on the usage of Mahout. Mahout helps in clustering, which is one of the most popular techniques of machine learning. Clustering allows the system to group numerous entities into separate clusters or groups based on certain characteristics or features of the entities. One of the best examples of clustering is seen in the Google News section. In the next screen, we will continue discussing the usage of Mahout. Another concept of machine learning is collaborative filtering. Mahout enables collaborative filtering. Collaborative filtering is used where data mining is performed for recommendation engines. Examples of collaborative filtering can be found in shopping websites where data is displayed depending on the user's browsing experience. One such example is shown on the screen. In the next screen, we will focus on Apache Cassandra. Apache Cassandra is a freely distributed, high-performance, extremely scalable, and fault-tolerant post-relational database. It has the following features. It is designed taking into consideration that system or hardware failures can occur. Cassandra follows read or write anywhere design, which makes it different from other ecosystem components. The benefits of Cassandra are that it performs online transaction processing or OLTP operations and online analytical processing or OLAP operations, and it helps to modify real-time data and perform data analytics. In the next screen, we will discuss why Apache Cassandra should be used. Apache Cassandra is used for the following characteristics. It has direct features to scale from gigabyte to petabyte storage. It improves performance with the addition of nodes. It has no single point of failure. It allows easy distribution and replication of data. It supports multi-data center and is cloud capable. It supports multiple languages and platforms. It can directly work in commodity hardware and does not require any special hardware. In the next screen, we will focus on Apache Spark. Apache Spark is a fast and general MapReduce-like engine for large-scale data processing. Following are the key advantages of Spark. Firstly, Spark has speed. Spark claims to run programs up to 100 times faster than Hadoop MapReduce in memory or 10 times faster on disk. Spark has an advanced DAG execution engine that supports cyclic data flow and in-memory computing. Secondly, Spark is easy to use. It offers support to write applications quickly in Java, Scala, or Python. It offers interactive Scala and Python shells. Thirdly, Spark provides generality. It can combine SQL, streaming, and complex analytics. It powers a stack of high-level tools, including Spark SQL, MLlib for machine learning, GraphX, and Spark Streaming. Fourthly, Spark is integrated with Hadoop. Spark can run on Yarn Cluster Manager of Hadoop 2 and can read any existing Hadoop data. In the next screen, we will focus on Apache Spark tools. The key tools of Apache Spark are as follows. Spark SQL is used for querying structured data as a resilient distributed data set or RDD in Spark with integrated APIs in Python, Scala, and Java. Spark Streaming has the provisions to read data from HDFS, Flume, Kafka, Twitter, ZeroMQ, or custom data sources, and is used for stream processing written in Java or Scala. GraphX is used to view the data as both graphs and collections, transform and join graphs with RDDs efficiently, and write custom iterative graph algorithms with the Pregel API. MLlib comprises a library of algorithms including regression, classification, clustering, recommendation, singular value decomposition, and feature transformations. In the next screen, we will focus on the key concepts related to Apache Spark. Apache Spark revolves around resilient distributed data sets, RDD, which are fault-tolerant, read-only collections of elements that can be operated in parallel. Following are the features of RDDs. RDDs are cached in memory or disk. They support various operations including transformation, for example, map, filter, distinct, union, samples, join, reduce, and so on. RDDs also support actions, for example, collect, count, first, for each, and others. Spark has an easy API for writing programs in terms of transformations on data sets. It supports user-defined functions or UDFs. Spark has an interactive shell for iterative development. In the next screen, we will further focus on Apache Spark. An example of a program written with the help of Spark interface is given on the screen. In the next screen, we will focus on Hadoop Integration. Apache Spark supports the Hadoop deployment model, among others. Some of the deployment models include standalone deployment, Mesos-based deployment, and Yarn-based deployment. Spark can be deployed on existing Hadoop clusters and also be run just as another Yarn job. Spark offers data compatibility to Hadoop. It can access HDFS data and use compatible data input and output formats as in Hadoop. Spark leverages localized data processing. Let us summarize the topics covered in this lesson. The Hadoop ecosystem is categorized into components such as file system and data store, serialization, job execution, and others. Oozie is a workflow scheduler system used to manage Apache Hadoop jobs, MapReduce jobs. Mahout interacts with Hadoop services to perform machine learning processes. Yarn has the capability to perform resource monitoring and allocation with scheduling. Apache Cassandra is a freely distributed, high-performance, scalable, and fault-tolerant post-relational database. Apache Spark is a fast MapReduce-like engine used for large-scale data processing. In the next lesson, we will focus on Hadoop administration, troubleshooting, and security.